In this section, I'm going to talk about curvilinear motion, polar and cylindrical coordinates. Polar coordinates are often used to describe the curvilinear motion of a point. Circular motion, certain orbit problems, and more generally central force problem, in which the acceleration of a point is directed toward a given point, can be expressed conveniently in polar coordinates. Let's look at some application of polar coordinates in real world. For example, fire truck ladders can rotate as well as extend. The motion of the end of the ladder can be analyzed using radial and transverse component. Another example, by knowing the distance to the aircraft and the angle of radar, air traffic controller can track aircraft. Consider a point P in the x and y plane of Cartesian coordinate system. We can specify the position of P relative to the origin either by Cartesian coordinate xy or by its polar coordinates r and theta. To express vector in terms of polar coordinates, we define a unit vector er that points in the direction of the radial line from the origin to P, and a unit vector E theta that is perpendicular to ER and points in the direction of increasing theta. In terms of these vectors, the position vector R from O to P is RER. Notice that R has no component in theta direction. We can determine the velocity of P in terms of polar coordinate by taking the time derivative of RER, and acceleration is derivative of velocity respect to the time. This is the mathematical derivation procedure for velocity and acceleration. However, the conclusion is important. If the motion occurs in the xy plane of Cartesian reference frame and theta is the angle between the x-axis and unit vector ER, the unit vector ER and E theta are related to the Cartesian unit vector by ER equal cosine theta I plus sine theta j, and E theta equal negative sine theta I plus cosine theta j. Look at this coordinate system. The curvilinear motion represented in three-dimensional cylindrical coordinate system. As you can see, we keep the same z-axis from the rectangular coordinate system, and we replace 2D x and y coordinate system by 2D polar coordinate system. Therefore, the position of this particle can be represented by r, theta, and z. There are three unit vectors associated with three-dimensional cylindrical coordinate system. ER, the direction of the radial component, E theta, the direction of transverse component, which always perpendicular to ER, and EZ, which is the same k unit vector in rectangular system, and EZ always perpendicular to the plane that made by ER and E theta. You can find the velocity using this formula, and also you can find the acceleration by using this formula. I skipped the mathematical derivation procedure here because the conclusion is it's important. Let's look at two examples. Rotation of the arm about O is defined by theta equal 0.15 t squared, where theta is in radians and t in second. Cola B slide along the arm such that R equal 0.9 minus 0.12 t squared, where r in meter. After the arm has rotated through 30 degrees, determine the total velocity and total acceleration of the collar. This is our plan. First, evaluate time when theta is 30 degrees, then evaluate radial and angular position and first and second derivatives at time t, and finally find the velocity and acceleration in cylindrical coordinate. First of all, we have to convert degree to radian by this equation and find the time. The total time for rotating arm 30 degrees is 1.869 seconds. Now we have to evaluate radial and angular position and first and second derivative at time t. After we find the radial and angular position and first and second derivative at time 1.869 seconds, we can calculate velocity and acceleration from equation that mentioned earlier. This is the total velocity that we find from this equation, Vr and V theta, and this is the total acceleration that we find from AR and A theta. Let's look at next example. The angular acceleration of the centrifuge arm varies according to theta double dot equal 0.05 theta. If the centrifuge starts from rest, determine the acceleration magnitude after the gondola has traveled 2 full rotations. First, we have defined our coordinate system. After that, calculate the angular velocity after 2 revolutions. Next step, calculate the radial and transverse acceleration, and finally find the overall acceleration magnitude. Okay, we solve this problem in polar coordinate system. First, we have to determine the angular velocity. As you can see, the acceleration is a function of position. So we have used this equation. This is the third kinematic equation. For finding angular velocity for two full rotation, we have to take integral from this equation. When we integrate it from both sides, we find the angular velocity. This is angular velocity for 2 full rotation. Also, we have the radial that is 8 meters. We can find the radial. Now we can find the radial and transverse acceleration by this equation. And finally, this is the magnitude of the acceleration. Thank you for watching.